the next talk by Mathilde Bouvier. I hope I have pronounced the name more or less okay.
Yes.
So she is a postdoc researcher at the University of Grenoble. And I think she's studying fruits because she will talk about oranges and peaches. And we will learn about the chemical nature of protostars in Orion. Let's see.
Sorry, I will share another screen. You can see my screen now?
Now we can see it well. Perfect.
Okay.
All yours.
Thanks. So hello, everyone. And of course, thank you for the organizers to giving me the opportunity to share the results I'm going to tell you today. So I will speak about the chemical nature of Orion protostars, and indeed I will compare oranges and peaches, and I will explain to you why in a minute. First, let's go back to how we form a solar mass star form. So you saw this kind of schema this morning already, so I will go fast on that. So the onset of star formation starts at the prestellar core phase, where there are these dense and cold fragments of molecular cloud that eventually collapse. The temperature at the center of these fragments increases until the central object is born. This will be the future star, and it is surrounded by an infilling envelope of dust and gas. At the same time, there is also usually bipolar outflows where material is ejected. Once the envelope dissipates, what remains around the central object is a protoplanetary disk where planets can eventually form. And once all the material has been used to form these planets, we have the final planetary system. In astrochemistry, what we see is that there is an increase in the molecular complexity from the early stages of the star formation up to the later stages. And in particular, in our solar system, we observe the highest level of molecular complexity that has been achieved with the life on Earth. So one of the big questions in astrochemistry is to understand whether the molecules that are crucial for life were the ones formed at the early stages and survived all the journey or not, or if there was some kind of reprocessing along the way. In the following of my talk, I will focus on the protostellar phase because this phase is particularly chemically rich. This is where most of the complex molecule will form. And in fact, what we see is that not all protostars share the same chemical content. We have two chemically distinct type of solar mass protostars. So on the one hand, we have what we call hot corinos. These objects are dense, hot, and compact, and they are enriched in what we call ICOMs, so interstellar complex organic molecules, such as methanol, dimethylether, formamide, and so on. On the other hand of the spectrum, we have the warm carbon chain chemistry sources. So these protostars have their inner regions that is deficient in ICOMs, but they show a larger zone that is enriched in carbon chains and rings. The question is, why is there such chemical diversity? So the main, what we think is that at the prestellar core phase, so the phase before, there is a chemical variation of the ice mantle around the grains. So and this chemical difference, we have two main hypotheses that could explain why the ice composition would be different. So the first hypothesis is the difference of time scale of the prestellar core phase. So you have the gas, your grain, which is surrounded by the ice mantle, and in the gas phase, you can have two main scenarios. So for example, for a short prestellar core phase, the carbon atoms don't have time to lock into the CO molecule. So they will deplete alone onto the grains. Then on the grains, there is the major reaction, which is hydrogenation with the H atoms. So the reaction between the carbon atoms and the hydrogen will form mostly methane. So we will have methane-rich ice surrounding those grain. Then going from the prestellar core phase to the protostellar phase, the temperature increases. So the ice mantle will evaporate and the molecules liberated into the gas phase. And so the methane that was trapped onto the ice mantle will sublimate and react with other molecules to form carbon chains. And we will have a WCCC protostar at the protostellar phase. On the other hand, if the prestellar core phase is longer, we will have in the gas phase mostly CO molecules, which are going to deplete. And again, with the hydrogenation process, we will have instead a methanol-rich ice in particular. And once the ice sublimates, the methanol will react in the gas phase and produce other ions. And at the protostellar phase, we will have a hot corino. The models can reproduce hot corinos and hybrids, which are a hot corino surrounded by WCCC zone, but they cannot reproduce pure WCCC. The other hypothesis is the UV radiation during the prestellar core phase. So if we take our prestellar core that is subject to external UV radiation, the UV photons will break up the small molecules, so in particular CO. So in the gas phase, we will have mostly carbon atoms. Again, the carbon atoms will deplete onto the grain surface, and we will have, in that case, a methane-rich ice. If the core is shielded, we will have in the gas phase mostly CO molecules that will deplete onto the grain surface where methanol-rich ice will be able to form. And there is the intermediate phase where, in the case of non-uniform UV illumination, we can have a mixed composition of the ice mantle. So this is at the prestellar core phase. So then, depending on the composition of the ice at the prestellar core phase, we will have either a WCCC or a hot corino protostar. And in that case, the models can reproduce pure WCCC sources. So in the following, in our study, we focused on the environment. Can the environment affect the chemical composition of protostars, and how? So to do that, we need to study solar mass protostars chemical composition at small scale, because we don't want external contamination. So we need interferometry, and in different environments. And this is the cause of peaches and oranges. So peaches and oranges are two ALMA surveys at 1.3 millimeter. And they have the same sensitivity, spatial resolution, and spectral setup. So they are made to be compared directly. Oranges is Orion ALMA New Generation Survey. We targeted 19 solar mass protostars located in the OMC23 filaments, which is considered as a dense protocluster, highly UV illuminated. On the other hand, Peaches Perseus ALMA Chemistry Survey targeted 50 solar mass protostars throughout the Perseus molecular cloud, which is considered as a much looser protocluster and less UV illuminated. In the case of Peaches, they found that hot corinos are relatively abundant. So they have almost 60% of hot corinos in the region. So we were wondering what was the case for oranges. Since Peaches focused on hot corinos, I will focus in the following only on hot corinos. I won't talk about the WCCC sources, but you are welcome to ask questions if you want. So this is the filament, the OMC23 filament. And as you can see, it is particularly interesting because it is surrounded by 3 H2 regions. So it is highly UV illuminated. This is what we are interested in. And until our study, there were 3 non-hot corinos in the regions that are shown within the red frames, and no WCCC sources. So with oranges, we targeted 19 solar mass protostars. So none of them included the hot corinos that were discovered previously. And we targeted 1 species with ALMA, so methanol, because it's the simplest icon that is found in hot corinos, and it's the most abundant one. So we aim to understand whether the hot corinos are abundant in this region. So we detected methanol towards the center of 5 protostars. So here on the left, you have in red contours and gray and black, in red shaded area, colors, gray and black contours, the dust continuum emission, on which I overlaid in green contours the moment zero map of one of the methanol transition. So you can see that depending on the sources, the emission is not always resolved first. And also in some sources, the emission is relatively extended. But so here are the maps only of the transition at 45 Kelvin. So it could trace other, like the outflow, for example. But I had a higher upper level energy level emission, which are all compact. And using these methanol lines, I could derive the gas physical conditions using a non-LTE large velocity gradient analysis. And from this analysis, we found that the methanol is emitted in a region that is relatively dense, hot, and compact. So if you remember, this is the definition of a hot corino. So we detected 5 new hot corinos in the OMC23 filament. So based on 19 initial sample sources, it leads to a detection rate of hot corinos of 26% in OMC23. So it seems that hot corinos are much scarcer in a highly UV illuminated environment. So it seems that oranges are different than peaches. But there is one caveat, which is the high statistical error that you can see due to the fact that we have only 19 solar mass protostars. So unfortunately, we could not firmly conclude, but we have a clue that the two regions could be different. Also, there is a recent paper from De Simone et al. 2020 that showed that if the dust is optically thick enough at a millimeter wavelength, it can totally obscure the presence of hot corino. So we wanted to understand if if dust could be the main parameter affecting the detection of hot corinos in the OMC23 filament. So for that, we compared the velocity integrated intensity of one of the methanol transitions as a function of the dust optical depth that we derived in a previous paper. So the field colored rectangles are the 5 hot corinos that I showed you before. And among the other sample sources, here are the other one where we do not detect methanol. So we have only upper limits. If the dust was a main parameter affecting the detection of hot corino, we would expect an anti-correlation with hot corinos having being the sources where the dust is optically thin. But this is not the case because we don't see any anti-correlation. So the dust optical depth does not seem to be the main parameter affecting the detection of hot corino. But as you can see, thank you. As you can see, there are 4 sources for which we previously derived upper limits for the dust optical depths that are larger than 1. So we cannot exclude that in these sources, the dust could still affect the line emission of ICOMs. So we don't know whether these sources, we cannot conclude whether the sources truly don't have hot corinos or not. So the initial question was, are oranges different from peaches? So we found that there are only 26% of hot corinos in the OMC23 filament. So it seems that hot corinos are much scarcer in Orion than in Perseus. So in a region that is more highly UV illuminated. And apparently the dust optical depth is not the main parameter that affects the detection of hot corinos. So oranges seems to be different than peaches, and the environment may be the culprit for shaping the protostellar chemical nature. But we also identified 2 main caveats. The first one being that we have a large statistical error in oranges. So there is still a doubt on the difference of the 2 regions. And also for some sources, since we have dust optical depths that could be larger than 1, we are not sure that there is no hot corinos hidden behind. So we will need to do follow-up studies to increase the statistics and try to understand whether the dust affects the sources in the case of where the dust is optically thick. So stay tuned, and I'm done already.
Thank you so much for the talk. So it's good that oranges are different to peaches. That's a very important conclusion. I have some questions. I don't know if there are some questions in the
No,
chat.
you can go ahead while people are thinking.
Okay, so I have one that it's so for the hot Coriolis in Orion. So do you see if they are located closer to the ionizing sources, so to the places where the ionization could be larger?
Yes, so the sources of Coriolis are Simba A, MMS5, MMS9A here, FIR-CCA, and CSO33B. So they are more or less all along the filament. Yeah, so they are not correlated with the position of yes, UV radiation.
That's interesting. Yeah. Can I continue asking questions, Marcella? Or?
Sorry, we have a couple of questions.
Okay, then I shall.
So one is from Fernando Kulsa, has two questions. Which other species did you target in your spectral setup?
So I, in terms of ICOMs or just carbon chain, so I can say for ICOMs, so we have methanol, acetaldehyde, methylformate, dimethyl ether, most of the main ICOMs that were that are usually detected in hot Coriolis.
And what is the inclination of the disks that you targeted? Are they most face on or edge on? So I don't think we can. So we don't resolve the disk, I would say. There is only these two sources where there are observations, the dust observations from Tobin 2020 that I think resolve the disk. And this one would be elongated like that, and here too, but they did not conclude whether they were edge on or face on. So I mean, with ALMA now, I don't think we can disentangle the disk, really see the disk. If you have another for one question,
I have. Yeah, there is time for more. Yeah.
For environment condition, you stated about UV irradiation. Are there differences between Orion and Perseus regions with respect to their galactic positions, galactic plane, or galactocentric distance? Orion is further away than Peaches. Peaches is between 200-300 parsec, and Orion is almost to 400 parsec. But the main difference concerning the UV radiation is that Perseus forms only low to intermediate mass protostars, while Orion forms also massive stars. So this is the main difference between the two regions. Then, depending on their location, they are below the plane. So I wouldn't say they are so much, and on the external part. So I don't think they are really different in that sense. No other questions from the chat.
Okay, then I take the time to ask another question of the list of 5 or 6 that I have. So the other is so you were talking about the hot Coriolis. I guess the other protostars that you identified in Orion or in Perseus, not all of them are BCCs, right? So they are probably protostars without chemistry to be classified as hot Coriolis. Could you say a little bit the percentages of these different types of protostars?
So in fact, with these ALMA observations, we could not conclude whether in Perseus or in Orion about the WCCC protostars because we were probing too small scale. So we were resolving out most of the WCCC zone. So we could identify only the percentage of hot Coriolis, but not the other types of protostars.
Okay, I see. So we need more ALMA data. That's always good. Okay, so we will post the questions in the Slack channel and I will write for you a couple more, yes, that I want to know. But thanks again for the nice talk.